Grab your phone. It has 3 natural axes, you can spin it around.
Watch what happens with each one, because one of them does something deeply strange.
Spin it about its long axis, the way you'd twirl a baton. Clean. Stable. It just spins. Spin it like a frisbee, flat about the axis through its face. Also stable. No drama.
But now spin it about the axis through its side, the intermediate one, in between the other two.
Try it. It will not stay put. It flips. Then flips back. Over and over, all on its own, with nothing touching it. 2 of the 3 axes are rock-solid stable. The one in the middle always tumbles. Astronauts have watched it happen in orbit. And the reason why is a beautiful piece of mechanics. Let's be fair to the textbook answer. It's not wrong, it's incomplete. So let's see exactly what it explains, and what it quietly skips. Here's the catch. That conservation law only holds when there's no external torque. But gravity is absolutely applying a torque here, pulling down on the wheel, hinged at the pivot. So angular momentum here isn't even constant. It's being changed, every instant, by gravity. So the real question was never whether angular momentum is conserved. It's this: gravity is changing the angular momentum. In which direction does it change it? Your gut says gravity should tip the angular momentum downward, so the wheel drops. But in reality, gravity turns it sideways. Answer that, and you've explained precession completely. And to see why it goes sideways, we have to stop treating torque as just a number, and start treating it as a vector with a direction. First, the spin. A fast spinning wheel has a big angular momentum, L, pointing straight along its axle. That's the teal arrow. Now gravity. It acts at the center of mass, a distance or out along the axle, pulling straight down with force mg. The torque is their cross product, R cross F. And the cross product points perpendicular to both, so it's neither along the axle nor downward. Point your right hand along R, curl toward F, and your thumb points sideways. Horizontally. The torque from gravity is perpendicular to the spin, it points off to the side. Hold on to that one fact, because it's the hinge the whole explanation turns on. The torque points sideways, exactly perpendicular to the angular momentum. Here's the law that does all the work. Newton's second law, but for rotation, torque equals the rate of change of angular momentum. Rearrange it, and it says something simple but profound: the tiny change in angular momentum, dl, points in the same direction as the torque. Let's look straight down from above. The angular momentum L points outward, along the axle. And we just showed the torque, and so dl points perpendicular to it. So add dl to L. Because it's perpendicular, it doesn't make L longer or shorter. It just nudges the tip sideways, swinging the whole vector a little. Now repeat that, instant after instant. Every moment, the torque stays perpendicular to L, so every dl just rotates L further around. The tip of the angular momentum vector traces out a perfect circle. And that circling of the angular momentum vector is precession. The axle has to follow L, so as L sweeps around, the axle sweeps around with it. It never falls, because the torque never points downward, only sideways. Let's get the actual rate. In a small time dt, the torque adds a little dl, swinging the angular momentum through a small angle, d phi. From the geometry, that angle is dl divided by the horizontal reach of L, which is L times sine theta, where theta is the tilt from vertical. Divide by dt and you get the precession rate, capital Omega, the torque over L sine theta. Now substitute, the torque is mgr sine theta, and L is I times omega. Watch what happens to the tilt. The sine theta cancels top and bottom. Which means something remarkable, the precession rate doesn't depend on the tilt angle at all. And it leaves this clean result. And look where omega sits, on the bottom. So the faster you spin the wheel, the slower it precesses. That feels backwards, but it's exactly what you see. A fast gyroscope barely crawls around. Double the spin, and the precession rate is cut exactly in half. The math and the real gyroscope agree. Here's everything together, straight from the equations. A fast spin, a tilt, and gravity. The formula predicts it should precess at about 1.6 radians per second. And there it is, steady, stable precession. The axle sweeps around the vertical, never falling, exactly as predicted. But there's a subtlety. If you don't ease it in, if you just let go from rest, it doesn't glide smoothly. It dips, catches itself, and bobs up and down as it goes around. That bobbing is called nutation. Spin it fast enough and the bobbing shrinks to almost nothing, which is why a good gyroscope looks like it glides. The wobble is still there, it's just tiny. So that's the real story. Gravity's torque points sideways, perpendicular to the spin. So it turns the angular momentum sideways instead of tipping it down. And the axle simply follows. That, not a three-word slogan, is why a gyroscope doesn't fall.